I want to talk to you today about DDoS problems with internet-facing VMs. So who's here running Apache CloudStack with the VMs which have public addresses directly connected to the internet? And do you ever get DDoS attacks on those? Not really. Okay.
I'm very excited.
Yeah, so I'll tell you a bit about, so let's start about me. Everybody needs to have a slide out about themselves before you get started. So my current role is, next to being a parent and a husband, is CTO at Your Online. I'll talk a bit about Your Online in a moment, but I started my own hosting company back in 2003. Started using CloudStack at around 2010 when I was still part of cloud.com. Went through the whole process when it was adopted as an incubator product into Apache Software Foundation, and then finally became Apache CloudStack. My company became part of Your Online in 2018. Although I'm now CTO, we're all doing a lot of management stuff. I'm still a techie. So Linux networking, that's the stuff I really like, and open source technology is what I like. Don't get me started about IPv6. There's a footnote there. I did great. Yeah. I did a lot of talks about that. So I won't be talking about it today. But yeah, Ceph, CloudStack, and IPv6 are the things I want to see most. So Your Online, what do we do? Well, this is one of our fancy slides we have. We are a collection of hosting companies started in Europe, and we now have companies in Europe, in Canada, US, and we're doing more acquisitions over the world. It's not that they're all using CloudStack, but a large portion of our infrastructure runs on Apache CloudStack. We have two large deployments, one at the company you're hosting in the Netherlands, but they are actually internally servicing other companies running on CloudStack. And Axonet in Spain is doing the same. When we do Spanish acquisitions, which we did a lot in the last few years, we migrate away from Amazon to our CloudStack environment. All goes into our environment in Axonet in Spain. I am not controlling those environments. We have separate teams running the one in the Netherlands, running one in Spain. I'm just trying to nudge them into the right direction. I'm sending you presentations, what we see on conferences, but they are in control. We are running about, I think, 25,000 virtual machines directly connected to the internet, running distributed over these two CloudStack environments. So we do get a lot of DDoS attacks on those VMs. And that's what I want to talk about. So our services are public. We have web servers, DNS servers, email. You can have the list, but VPSs are the worst. Those are DDoS magnets, especially if you have unmanaged VPSs where customers just do their stuff on VPSs. You'll get a lot of DDoSs because they might be running Minecraft. And yet that's still what we do. You get DDoS attacks because the script kiddo wants to get the Minecraft server of the other one offline. Those things happen. And everything with us has public v4 and v6 addresses. So what kind of DDoS attacks do we see? Well, it used to be a lot of layer 3 attacks. So just bandwidth saturation. We would get DDoS in 400 gigabits, a terabit a second, to be sent just to our infrastructure, and we need to handle it. But nowadays you see more and more of the attacks shifting towards layer 7. And we do still see layer 3 and layer 4 attacks, and those are easier to filter nowadays, but the layer 7 attacks are becoming more and more of a problem. DNS amplification or many more attacks. You'll see Cloudflare writing that they handled another DDoS attack again of a few million sessions per second. And those are the types of attacks which we're seeing where CloudStack is suffering a bit. I think I don't need to explain the OSI layer to everybody here in the audience. I think that's quite common. So, but we have firewalls, right? We'll just put in a firewall and they'll protect me against the DDoS. If you go to any of the vendors like Cisco or Fortinet, they'll tell you, yes, get our firewalls and we'll protect you against the DDoS attack. My experience in 20 years, they don't. I tried a lot of them. They always say they can protect against DDoS attacks, but they simply cannot do that. You need to go to specialized companies like Arbor. But if you go to companies like Arbor Networks, if you get your layer 3 attack and they'll be sending you a terabit per second, there's no way you have a terabits of capacity to handle that incoming DDoS attack. So you will need an external service to do something about it. But the other attacks, layer 7, maybe they can help you with it, but let's move forward to where actually CloudStack is suffering. But then with a firewall, they can get saturated, bandwidth exhaustion, concurrent sessions, packets per second. Let's get a bigger firewall. There will be somebody with a bigger gun. That's the reality. So you can get a better firewall. You might be able to survive a bit more attacks, but you'll suffer an attack at some point, which you cannot filter away. Local firewalls are not sufficient. And it just takes one DDoSer with the tool hping3. Somebody ever used the tool? Legitimately, I guess. Yeah.
Just for testing.
Just for testing. Just for testing. No, and there are a lot of networks out there which do not implement BCP38. Now, let me explain BCP38. That's a networking best practice, which says that you need to do filtering on your outbound packets out of your network. By default, a router will never look at the source of an IP packet leaving your network. So if your host just sends a packet with a spoofed source, your router will just forward it towards the destination if there's no configuration on there. So you'll see a lot of amplification attacks where somebody sends a small request to a server, and the server actually what says from bot, what says from victim, sends it to the server, and then the server sends back the request to the victim. If the request is much smaller than the answer is, that's what we call an amplification. So if your request would be a few bytes, but the answer will be hundreds of bytes, it's very easy to overload a victim by just having a few servers sending traffic and overwhelming the victim with a few hundred gigabits of traffic coming in. Now, one of the great things is with CloudStack, if you're using the security groups, it will do the source checking. So VMs running on CloudStack cannot send spoof packets because the hypervisor will filter away the traffic. Talking about KVM here. My knowledge is about KVM. I cannot talk about VMware nor Zen. So this is all KVM. And so it helps to prevent that you are participating in a DDoS attack. It doesn't protect you against a DDoS attack, but you're making the internet a bit better place. But if we start looking at the security groups of CloudStack, looking at a KVM hypervisor, if you look at the IP tables, and now we have this beautiful screen where the interesting part is at the bottom of the screen. So this is one of the IP table lines saying that all kinds of traffic is allowed in, ingress port 8080, well, all kinds of ports. And then we also say that any packet in the related or established state is allowed to go into the VM. That means that we're doing stateful connection tracking on the hypervisor. So every packet going in and out is being tracked by the hypervisor, ensuring that the VM can communicate. Why? Well, if you know how TCP works and how UDP works, you would see that connections being initiated from VM going out will use a source port of something like 65,000, 63,000, but those packets are not allowed to go back into the VM. But if the hypervisor is tracking the connections going out, it goes, the hypervisor, the VM just sent a packet with source port 63,000. I need to allow this packet in again for the same session. So we start tracking all the connections on the hypervisor. Brilliant, right? Because otherwise, on the ingress, we would need to open a certain range of ports, which we then need to match with our TCP settings on the VM. Now, seems all fine. But if you have stateful filtering, we keep track of the state of the network connections and it monitors every session. But stateless filtering doesn't do so. So every packet is considered individually. So you would say, let's go for stateless, but I just explained that it's not possible in the current setup. So the downsides of stateful connection tracking is that you'll have table limits on the hypervisor. So you're building up a table of all the connections going through, and that consumes memory. But if you have a DDoS attack, you could have a state table exhaustion happening. Imagine somebody spoofing packets and sending random source addresses to your virtual machine, thousands of packets per second. Each for your hypervisor is a new session. So it just adds a new entry into the table of your hypervisor. It would be a DDoSer. Just I took this screenshot quickly from Google somewhere, but using hping3 saying flood, and then you could use random source addresses towards a victim, and you could overload the hypervisor within a couple of seconds. Doesn't matter how much memory the hypervisor has, the default connection tracking table can have about 256,000 connections, and then it will be saturated. You'll reach that very quickly. Or somebody just using it again, a flood, UDP mode, just sent UDP traffic to port 80, super easy UDP, just overload the connection tracking on that VM. or on the hypervisor. Looking in your hypervisor, this is what you'll notice. Does it ring a bell to somebody seeing this in your kernel logs? Well, this will happen on the hypervisor. And the problem is that this affects all the virtual machines on the same hypervisor because the connection state is tracked globally for all the VMs on the same hypervisor. Now, we are running hypervisors with 1 terabyte of memory. And if you have 4 gig of memory for a VM, you can run 200 virtual machines on the same hypervisor. So one VM getting a DDoS attack, which would just be a lot of packets per second, would lead to exhaustion of the state table, would then lead to all the VMs going offline. Now, this is only true if you're using shared networks, because that's where the hypervisor does the packet inspection. It's even worse if you're using a VPC with a VR, because then you have a VM running where all the traffic goes through. So we're bridging the traffic from the hypervisor into a VM, doing the state tracking, then getting it out of the VM again to the backing VMs. The VR will die quicker than a hypervisor will, but in the end, they'll both just get exhausted. But my experience with VPCs is limited. But this can affect other connections as well. If you set up a firewall on the hypervisor, which does the connection tracking, which you probably are doing, then it can also affect your NFS 7 iSCSI traffic or your Linstore DRBD traffic. It should have added them to the list as well, because it's TCP traffic is being inspected. So what you will see is that you'll get a DDoS attack, but then suddenly also your VMs are struggling with getting connection to their storage because it goes over TCP IP as well. If you carefully craft your firewall rules, excluding your storage traffic from connection tracking, you might be able to do that, but that makes you need to configure that on IP tables. Otherwise, you'll suffer from this. But with a lot of connections coming in per second, you will just run out of memory very, very, very quickly. So, do I have a solution? Well, sort of. So, don't host DDoS magnets. It's that easy, right? No, seriously. Minecraft servers, Tor exit nodes, certain kind of websites, they are just magnets for DDoSes. But what we also see is that we host e-commerce websites. We see a small DDoS attack going to a web shop. Then the owner of the web shop gets an email saying, hey, we just did a test. We showed you 15 minutes of downtime. You need to pay a couple of Bitcoin. Otherwise, your website will be down for 24 hours. If you don't pay, we'll make it 48 hours, make it 72. You'll just stay offline until you pay us. So this digital extortion also happens. So there's mafia on the internet doing this. Now, you can invest in upstream anti-DDoS services, which can do filtering for you, but it goes to a certain limit. They cannot filter everything for you. If you have a small attack coming in with packets per second, let's say, or connection per second, a couple of thousand, it's not that they're always able to filter this for you. And you can improve the security groups in CloudStack. So let's dive into that part. We did some manual patching locally, which we are willing to share, but it's just simply not going to apply to the community. Somebody hacked the security group.py script to make it a bit more workable for our situation. Again, not a secret, but just simply not applicable to the broader community. Well, we can't fix everything with CloudStack. So let's be realistic, because if you get a major DDoS attack, it's not that CloudStack can fix this for you. But there are things which we can, I think, improve in CloudStack, and that's making the security groups modular inside the KVM agent. It's currently hard-coded that it executes a Python script, which then starts programming IP tables locally on the hypervisor. But there are certain scenarios where you probably want to implement a different way of filtering, where many just would like to use the default security groups, but others might want to use a different method to achieve the same end result. So CloudStack would just be saying to the driver, make sure these rules are programmed. The driver would say, yes, done, and then it's no longer CloudStack's concern. So I have a few ideas where we could look at. So eBPF. If you go to any Kubernetes meetup, you should go there. That's all they talk about. Fascinating. All the companies are trying to sell you stuff that they'll have the magic word eBPF, but it is very interesting. You can run packet filtering inside the Linux kernel, which gives you way better performance. Because going back to IP tables, and I have a link, I think, later in the presentation back to this. If you look at these rules, IP tables goes through them sequentially. Doesn't match, doesn't match, doesn't match, doesn't match, doesn't match. for every packet that goes through sequentially. That was fine when we're still talking with modems of 128K, you know, dialing into the internet. That was fine. But nowadays with links, 100 gigs, 400 gigs, it is not fast enough anymore. So IP tables is becoming a problem with performance. So that's why everybody is switching to eBPF. And that's also the reason why we have certain services like our DNS servers running on bare metal, filtering with eBPF, because running those VMs inside CloudStack is simply not doable due to the performance restrictions IP tables are giving us. So, but all kinds of NICs can do hardware filtering of packets. So wouldn't it be beautiful if you would have a driver in addition to the default driver, which can program your network card and then do the filtering on the network card before it even reaches the hypervisor and the virtual machine running on there. But it could also be a combination, of course. So as I said, tiered filtering. So make the first line of defense stateless. Do that with eBPF or on the network card. Then hand over the packet to the operating system to the later inspection. But you can filter away most of the DDoS attacks just on the bare metal on the network card. We did a few tests with Power DNS. We are running some Power DNS services on bare metal with eBPF. We're able to handle about 1 million concurrent sessions or 1 million packets per second on a single bare metal machine, which is just a fairly cheap machine, just serving DNS answers. 1 million packets per second on just a normal machine using eBPF and modern network cards. And I think that's something where CloudStack can really improve, making the security groups better. So or a custom solution, you implement your own driver in the agent saying, I'm a smart guy, I know how the stuff works. I do video streaming, I do all kinds of stuff. I'll just implement my own security groups, but we should make it modular because the current implementation says you need to use Python with the IP table rules and it simply doesn't work for everybody. So it might be a combination of these. And oh yeah, there's something down below. Why also the kernel community is replacing IP tables by eBPF. It's interesting to read from a couple of years back why we are moving away from IP tables. So is it going to be easy? No, I don't think so. It's not going to be easy. So therefore I'm proposing that we go to a driver model where we can experiment with an additional driver to the existing implementation. So making a driver model first, existing implementation is the primary and probably going to be the only driver for a while, but to give people the flexibility to come up with a brilliant idea, implement an additional driver, and just start experimenting. Because if it's a driver, it's also much easier to experiment in a lab. Otherwise, we need to think about migration scenarios where you go from the old to the new situation and just give people the idea, say, okay, if you want to use a different driver, you need to shut down your VM, all your VMs and boot them up again at a certain maintenance windows, and then they're using the different driver. But we can also improve the current implementation. As I said, we are tracking all the packets going into the VM. Our implementation, which we have, where we do no tracking for certain connections, and we're all seeing good results. So I'm happy to post those on the mailing list. But again, it's a hacky situation just for our local deployment. So modularity would be very welcome. And then I'm asking for volunteers. Anybody who thinking about implementing this? But any feedback? How are you experiencing this with the security groups on KVM? Any? Because I saw you nodding a couple of times, saying, "Yeah, you experienced this."
We don't filter on the hypervisor yet, because we're just from the end of CloudStack, and we have our firewalling completely separate dedicated hardware. But the first thing that came to my mind is why would I ever want to filter on the management network, which is not connected to anything that anyone could ever access. So a loss of storage should be a problem. And then the first idea would be can make compartments for separate IP tables, resources per VM.
I looked into that part. If you could have a separate connection tracking table per VM, there's no implementation in IP tables who could do that, because I was brainstorming with a colleague of mine saying, okay, what kind of ideas can we come up with? But yeah, we came up with together with this engineer saying, oh yeah, we can do no tracking on certain elements. So yeah, he hacked a Python script within 30 minutes saying, I'll just inject a few lines here and hey, it works great, and he never touched it again. But yeah, that's how it often goes, right? We can how hacky things go. But we do have a few additional things. What we do as you're online. I'm not going to tell everything how we do our anti-DDoS, because this is going to go public and I don't want a DDoSer to know how we do all our anti-DDoSing. But we use a combination of a few things. So we have flow analysis on the incoming packets on the border routers outside on the network. That's being sent via S-flow to FastNetMon. It analyzes certain patterns of traffic coming in towards the addresses. And then we can filter a specific /32 or 128 or v6 of traffic coming in. We have dedicated hardware machines. We just have 100 gig NIC, one port connected directly to the border routers. And if we then inject the BGP route from FastNetMon, we can reroute that single IP through these machines. And on those machines, we have eBPF filtering certain types of traffic away, which we do not like. And if we see a certain DDoS attack, an engineer can just say, okay, I want to block all the source packets coming from a certain IP or to a certain destination. Often you see, and I think that all the script kiddies are so stupid, they're sending DDoS attacks with a fixed length of packets. So all the packets they're sending are like 80 bytes. I'm like, oh, okay, let's just filter all the packets with the source 80 bytes or the size of 80 bytes heading towards this IP address on port 80, and then you filter a 99% of the DDoS attack. Often they're so simple. So we have dedicated machines doing that. Again, not super special machines, just Linux machines running with BGP daemon, and that's it. If it becomes too difficult, we offload it to external carriers. And so if we get a very large DDoS attack, then FastNetMon would inject a different BGP community, and the traffic is filtered upstream. So we send something to the upstream carriers, and they start filtering traffic within their network before it reaches us. Yeah, but that is of course different from CloudStack. But that's the way we use a tiered security. But I do think we need to improve in CloudStack, because we can do much better in CloudStack. But it will also give better VM performance, lower latency in the VMs, because IP tables simply is just processing all the traffic too slow. And this is one of the things you see with CloudStack. If you run a VM on CloudStack with just a lot of bandwidth, it will be suffering if you enable security groups. But for the end user, security groups is brilliant. Just say, I want to open these ports, API driven, great. But not so much if you're in a high bandwidth or high packets per second environment. So I think that was my feedback for today. So if you have any questions, this is where you can find me. So volunteers are welcome to implement a driver. Let's brainstorm about this. I do not think it's something we need to fix today, but going towards the future, we need to address the situation on the KVM. And I think going for modularity and giving people choices what to use for security groups would be the best. So hopefully somebody learned something today.